Hey, did you know that the number of murders in New York City is positively correlated with consumption of ice cream? So meaning, as those New Yorkers eat more ice cream, they actually commit more murder? I mean, who knew New Yorkers could be so die-hard over a pint of ice cream? Now, somebody new to statistics is often ready to jump in on the cause and effect bandwagon. You find a strong relationship between two variables, and you think there must be a connection. So let's think about why two variables might be correlated. Now, what about in our example? What is it that ice cream consumption and murder rates happen to have in common? Well, in our case, both of these tend to increase with temperature. So far, when we've talked about variance, we've really limited ourselves to one variable, right? Maybe we're looking at X or Y, but we've never put them together. But now, what if we have two variables and we think they might be related in some way, right? How do you think they might vary together? I mean, ice cream, murder, and temperature. So this brings us to the idea of covariance. And from there, today we're going to talk about correlation. All right, now let's look at another example. When my students study, as a professor, I really want to know, does their studying affect their grades? So, are my well-performing students just naturally brilliant? And other folks who study super hard, they still don't do well? Or is it that studying actually pays off in my classroom? Do my students who study actually get a higher exam score? Well, let's suppose I poll my class and I ask them, hey, tell me the total number of hours that you spent studying for your last STACS exam, and I get the following data. Hours studied range from 2 to 13. So 2, 3, 5, 6, 8, 9, 10, and 13. So what I'd really like to see is if studying has any relationship to their actual exam score. Well, lucky for you, I've brought their exam scores along. 58, 75, 71, 77, 80, 88, 83, and 95. We can actually plot this data in R. Here you see we've assigned X to our total time studied, so the hours studied, and that's that vector that we've used the C function to put those numbers together. In the same way, we've assigned Y to our test scores, and we're using the plot function to plot X versus Y. Now, we like a pretty plot in this course, so we're going to give it a title. Hours spent studying versus test score. And we're also going to label our X-axis and our Y-axis. So in this case, our X label is hours spent studying, and the Y-axis label is the test scores. And I actually changed the plotting character to 20 so those scores would actually show up a little bit better. Now you'll see there appears to be an increasing trend in time spent studying and test score. Notice that there's variability, right? So we see variability in two places along this graph. First, along the X-axis, and then also along the Y-axis. So there's variability in the test score, and also there's variability in the time that a student spent studying for an exam. Now, if we wanted to look at the variability in X first, here, look at this graph. We've placed a vertical red line at the mean number of hours spent studying, which in our data set is 7. So let's say we wanted to calculate the variance of X, right? Just looking at X. We'd have to actually calculate the distance from each of those points to the red mean line, square it, and then add them up. Right? Remember, this is our definition for variance that we talked about in the earlier lecture. Now here's a horizontal line at the mean of Y, 78.4. And this is the average test score for my class. Not too bad, but it sounds like a couple people might have been partying the night before, but I'm not going to judge. But if we want to calculate the variance in Y, well, we do the same thing we did for X. We're going to calculate the distance from each point to the horizontal red mean line. We're going to square them, and then we're going to add them all up. But now we have two variables. And so we're going to have to connect them, right? The way that we do this is by multiplying each X deviation by its associated Y deviation. And we're going to take the sum of those values. All right, here's how we're going to do that in R. We've got our vector X and our vector Y. Let's write out what that first deviation is going to look like. Okay? So we're going to take the first element in X, which is 2, corresponding to 2 hours spent studying, and subtract the mean, which is 7. We multiply that by 58, which is the first score on the exam, minus this mean, 78.4. Those two values are negative 5 times negative 20.4. And you see here, when you multiply them together, you get 102 as the first deviate. All right, let's keep going. What if we do it for the second point? We calculate the second deviate in the same way. Now it's 3 minus the mean of 7 times 75 minus the mean of 78.4 to give you a deviation of 13.6. Bring your attention all the way to the last point. The eighth deviation is 13 minus 7 times 95 minus 78.4. That gives us a deviation of 99.6. Now, if we take all 8 of these and we add them up and then divide by n minus 1, we get the covariance of our sample, right? So the covariance is really just telling me, how do X and Y vary together? How do they vary? The covariance of X and Y is equal to the sum of Xi minus its mean times Yi minus its mean, all divided by n minus 1. Now, again, R is going to make this so easy for you because it's already got a built-in covariance function called cov. Let's do that on our data set. Here you can see the covariance of X and Y is equal to 38. Now, formally, when we're thinking about covariance in terms of random variables, we can write it in terms of a random variable notation. And in this case, the covariance of X and Y is equal to the expected value of the quantity. So we're taking the product here of X minus its mean times Y minus its mean. Now, if we get a positive covariance, then that tells us that the random variables, they tend to move together, right? So if one random variable is above the mean, the other is also likely to be above its own mean. If our covariance is negative, it tells us that they move opposite of each other. So when one's above the mean, the other tends to be below it. Now, in our case, the covariance of X and Y is 38. Okay, so what does 38 mean exactly? I mean, is that a big covariance? Is that a small covariance? Is 38 relative to... You probably see the problem, right? So the covariance can take on any number of values. I mean, you might have a data set that has a covariance of 500, and I might have a data set that has a covariance of 5. And so unless our data is measured in the exact same units, we're not even going to be able to compare those two numbers. So the problem with covariance is that it can't tell us how strong the relationship is between X and Y. We've got to take it one step further. If we take the covariance and we divide through by the product of the two standard deviations, magic begins to happen. What we've just done is scale it to a dimensionless measure, meaning it has no units to it. I like to call it the dimensionless zone. But it's actually called the correlation coefficient. It's a popular way that we measure the strength of a relationship between two random variables. All right, here's how we get it. The correlation between X and Y is equal to their covariance, so what we just found, covariance between X and Y, divided by each of their standard deviations. So divided by the standard deviation of X times the standard deviation of Y. Now, in our case, the sample standard deviation of X and Y is approximately 3.7 for X and approximately 11.1 for Y. Here's how we would solve for our correlation. We'd take that covariance, 38, over the product of those two standard deviations to give us a value of 0.91 approximately. Now, this is a really strong positive relationship, and we can actually see that in the original scatter plot. We could also do this calculation in R by hand, right? So we've got our X and Y variables. We want to take the covariance of X and Y, so we can use the cov function, and we can divide by the product of the standard deviations using the SD function. So the cov of X and Y divided by the standard deviation of X times the standard deviation of Y gives us that same correlation coefficient. So you don't even have to do any work. In fact, what if you didn't even want to be that lazy? Like, what if you just wanted to do nothing and let R do all the work? It has a built-in core function. So core of X and Y matches up, gives us that same correlation that we calculated two other ways. Easy breezy. Now, you can think of the correlation as it's like a scale version of our covariance. And in fact, the correlation and the covariance, they always have the same sign. So either they're both going to be positive or they're both going to be negative. They're both going to be zero. Now, when the correlation is positive, we're going to say that X and Y are positively correlated, right? And likewise, when our correlation goes negative, X and Y are negatively correlated. That's kind of how I felt in high school when I broke up with my first boyfriend. We were negatively correlated. And as you could probably guess by now, if the correlation's zero, then those variables are going to be uncorrelated. So ultimately, covariance and correlation measure the linear dependence between two variables. Now, we refer to the population correlation using another Greek letter called rho. Not P, rho. It's got a little curvature to it. And so when we're talking about the sample correlation, though, we use the Roman letter R. So what does this tell you? Like if you're reading a stats book or you're doing a stats problem, or maybe you're looking at a graph and you see these two, when you see an R, maybe an R equal to 0.45, you automatically know that this correlation is being taken on a sample. Right? And then if you saw rho equal to 0.45, that automatically tells you that that correlation is on the entire population. Now, the correlation coefficient has key advantages over the covariance. Let's talk about a couple of them. First, now, unlike your covariance, our correlation is unitless, right? So it doesn't matter what kind of data you have or what kind of data I have. We can take the correlation and we can compare those numbers, like apples to apples. So that's one benefit. Secondly, now, since your covariance can range anywhere from minus infinity to infinity, it's hard to have an idea of scale, right? So I can get a covariance of 38 and not really know if that's big or small. So it's hard to compare. But for the correlation, we know that goes from -1 to 1. So we automatically, immediately have an idea of the strength of our relationship. Let's go back to our old faithful data set. This compared the waiting times of length of eruptions for the old faithful geyser. Now in R, we're able to calculate correlation for an entire data set using the core function. So we don't just have to put it on X and Y. We can insert our whole data set and it'll calculate the correlation for us. Now in this case, R gives us a 2x2 matrix. So we actually call this the covariance matrix in statistics. Now in the first column, you see that eruptions is perfectly correlated with itself, right? And it's also pretty highly correlated with weighting at a value of around 0.9. This second column, likewise, gives you the correlation between weighting and eruptions. And the correlation between weighting and itself is 1. So whenever you look at a correlation matrix, you're going to see ones along the diagonal. Now, inside the data set package is a data set called Harmon23.core1. And what this data set gives is the correlation between 8 physical measurements on 305 girls between the ages of 7 and 17. So what's really nice about R is not only does it have built-in data sets that we can look at and play around with, it even has built-in data that is just a correlation matrix that we can take, look at, pull apart, so we can really better understand how correlation works. So here's how we're going to load that data into R. If you don't already have it installed, you should first install the datasets library. Now you can do that in RStudio just by clicking on the lower right panel on Packages, then Install, and then type Datasets and press Enter. We then need to load and run the library datasets command so that we can bring it into our workspace. Now notice that along the diagonal, the values are all equal to 1. This is because each variable is perfectly correlated with itself. Let's find some of the higher correlations. So look here. In this data set, you see height and lower leg have a correlation around 0.86. Now, intuitively, this sort of makes sense, right? Because if I'm a tall person, then I'm likely to have long legs, right? So my height and my leg should be pretty correlated, highly correlated. Here's another one, arm span and forearm. These have a correlation of 0.88. Right, so this is also pretty logical, right? Since my forearm is actually included in my arm span, it makes sense that the two of them should be highly correlated. Notice here weight and this parameter bit row diameter. This is actually the width of the girl's hips at their widest diameter. Well, again, it makes sense that this would also be correlated, right? Because if my weight is low, it's likely that my hips are sort of small. Notice I said if my weight is low. Just put that out there. Here's some other correlations that are a little lower. Arm span and chest girth, correlated at 0.28. Okay, what does my arm span have to do with my chest girth? Apparently not too much, because those aren't very highly correlated. And look, surprisingly, height and weight only have a correlation of 0.47. Now, in statistics, height and weight, that's just like the bread and butter of statistics, right? Whenever you want to give an example of two things that are related, it's going to be height and weight. But here you see in this data set, it's less than 0.5. But one thing to remember here, right? Who's this the height and weight of? Exactly. These are girls ranging in age from 7 to 17. So this is the time when their height, especially, is going to be changing, and probably a lot faster than their weight. Now here's another fun data set in R, and it's in the car package. It's called Salaries. So if you don't have car installed, you can load that library using Library of Car. And then we want to pull up the data set Salaries using Data Salaries. And head just says, give me the first couple of rows just so I can see what this data looks like. So let's look at the head of this data set. Now, the Salaries data set is the 2008-2009 9-month academic salary for assistant professors, associate professors, and full professors at a particular college in the United States. And so they've collected this data so that they could better monitor salary differences between male and female faculty members. Me personally, I wanted to look at the data so I could go back to Harvey Mudd and tell him, hey, look, I don't make as much as this maximum person in this data set. So I needed a little evidence. So thanks for going along with me. All right, let's look at this data set. We've got 6 variables. They rank from professor, associate professor, and assistant professor. It also gives us the discipline and the years since graduating with a PhD, the years of service, and their gender. Now, summary statistics are going to help us get a better idea of this data set and its features. Notice in the summary statistics, we see that years since PhD ranges from 1 to 56, with an average of 22.3. Also look at this. Years of service ranges from 0 to 60, with an average of 17. All right, now here's where I would get on to my students if they didn't comment about that, because that 60 is likely an outlier. When we think about data maybe coming from an underlying distribution, normal distribution that is, we immediately know where our data should be located to be within 1, 2, or even 3 standard deviations of the mean. Now, when I look at data that has a mean of 17 with a minimum value of 0 and a maximum of 60, it tells me that that 60 is way outside of the probabilities for my normal distribution. Like, it's probably going to be a lot of standard deviations away from 17, especially if 0 is the other side, right? So I'd want my students to bring up that point and to make that connection. Notice also salary. Salary ranges from $57,800 to a maximum of $231,545. And that mean is around $113,000. We can calculate the correlation directly using the code you see right here. So in R, we can first find the standard deviation of our salaries data of the years since PhD. We'll call that SD.PhD. Second, we're going to find the standard deviation of our salaries data in years of service. Call that SD-Serv. Now, to calculate the correlation of those two, we're going to take the covariance, so the covariance of years since PhD with years of service, and divide it by their respective standard deviations. The value we get is approximately 0.9. Now, we could also use the R core function built into the R package. When we do the core of years since PhD with years service, it matches what we did by hand, 0.9. Now, we could also use R to calculate the correlation between all of the numerical values in the data set. Now, notice here I said numerical because you can't plug in a categorical variable and do a correlation of it. So let's create a subset of our salaries data, and this is only going to contain the numeric values. Here's what I've done for this plot. So here I've colored this plot for you based on rank. So the red points are for assistant professors, blue points represent associate professors, and green points represent full professors. Notice in the plot of years since PhD versus years of service, which is in the first column, the first plot, you see that there's a relationship between the two, correlated at 0.91, and you'll notice that most of the assistant professors are in the lower corner, followed by associate professors, with mostly full professors on top. In the bottom left corner, you see the relationship of salary with years since PhD. It also makes sense here that you would see a slight grouping of associate professors, assistant professors, and full professors as well. Notice that the correlation between salary and years of service is 0.33, and you see the corresponding plot. The correlation between salary and years since PhD is 0.42. Here on the next plot, we're looking at our salary data and the correlation by gender. Let's look at the first column. We've got years since PhD versus years of service. Same correlation of 0.91, but now we've colored the men as the blue dots and the women as the red dots. Now we have slightly more men in our data set, and so the blue dots tend to dwarf the red dots, but you can notice how our red dots are located around the 50% mark or below. Now, correlation and covariance measure the degree of linear association. If we have independent random variables that have a correlation of 0, however, it doesn't necessarily guarantee that we have independence. In fact, there might be a nonlinear relationship, such as data that's in a circular form, that would show a correlation of 0 even though there's a relationship between those random variables. Now, the R correlation coefficients, it looks for linear relationships, and it assumes that those two variables are normally distributed, but is not without its pitfalls. If you suspect a nonlinear relationship, we can actually consider transforming the data, maybe raising it to a log or an exponent. Remember, the correlation coefficient is just a single number, and it measures the linear association. But even that can lead to misleading results if you consider it outside of the context of your data. Take a look at these graphs. All of them have a correlation of 0.7, but their relationship is far from linear. So R is not going to stop you from getting a correlation of a data set, even if it's not really measuring a linear relationship. There's clearly a different relationship in your data. And one last pitfall, and I really want you to remember this. Correlation does not imply causality. So just because X and Y are correlated, it doesn't mean that X causes Y. They might both be caused by some other factor, or it could be that Y causes X instead. Here's a plot of cancer deaths versus churches. Notice that as the number of churches increases, so does the probability of dying from cancer. But do you think they really have a relationship? No, in fact, they're both correlated to the size of a population. Well, hopefully you're beginning to better understand the strength of the relationship between two random variables. And no, eating ice cream will not turn me into a killer, as long as they don't run out of butter pecan.